Okay, so we have one remaining topic, and that is the process of nuclear fusion. Nuclear fusion is the opposite of the two processes that we looked before, where we had the alpha decay and we had the nuclear fission. In both of those instances, the nucleus, a relatively large nucleus, breaks down into either a smaller nuclei, two smaller nuclei, or one slightly smaller nuclei with a small piece, the alpha particle, being emitted. Nuclear fission is the opposite of that. Instead of breaking large nuclei into smaller ones, we'll take small, lightweight nuclei and build them up to make larger nuclei. So we're essentially talking about the process that goes on inside the stars. And let's take a look at a couple of the reactions that occur, and then we'll talk about what happens inside of a star when we get to the chapter on astronomy. So there's two possible reactions that I would like to look at. Now there's a number of reactions, but we're just going to look at two, and both of them have the end product where they produce helium. So let's take a look at the first one. The first one is a process whereby a special form of hydrogen called deuterium. So this is not normal hydrogen. Normal hydrogen would be hydrogen 1. This is hydrogen 2. So this hydrogen has the one proton, but it also has one neutron. If I add two of these together, I will produce a helium nuclei, but not helium-4. I'll produce helium-3. Now, if you notice, the Z numbers are fine. I've got 2 on the left, 2 on the right, but I've got 4 protons, an atomic mass of 4 on the left, but only 3 on the right. This means that I need a particle which has no Z number, but 1 for the mass number, and that's describing, of course, the neutron. So this process produces helium-3, and as we saw with the fission process and with the alpha decay process, the mass of the guys on the left has to be more than the mass of the guys on the right, or otherwise we end up this reaction will not go naturally. If the reaction does not release energy on the right side, then it's not going to go. So let's take a look at the masses of each of these two particles. If you look in your table, which you should have your table in front of you, you will find in the second table that deuterium has a mass of 2.014,102, and of course we have two of these guys. So that's on the left side. On the right side, we have helium-3, and if you look that up on your table, you'll see that helium-3 has a mass of 3.016029, and the neutron, you can look up on your table, 1.08665. Okay, so let's go ahead and calculate 2 times 2.014,102. That gives a mass on the left side of 4.028204. And on the right side, we just need to add 3.016029 plus 1.008665. This gives us 4.024, slightly less, 694. So let's go ahead and calculate the mass defect. This gives us a mass defect of a mass defect of 0.00351 U's. Remember, this is the mass defect that we've just calculated, not the amount of energy. If I want to figure out how much energy, then again I can use that. Again, it's not a conversion, but it's effectively a conversion to figure out the equivalent energy of this much mass, And to calculate that, we treat it as though we are doing a conversion. That's 0.00351 U's. I know that 1 U is 931.5 MeV. And this gives us 3.2696. So for each reaction we get 3.2696 MeVs. If you remember from our previous calculations, this is a relatively small amount of energy. We had for the alpha decay 4.84 MeVs per reaction. For the fission process, we had something like 100, the radium fission, the uranium fission, we had 173 MeVs per reaction. Now the one thing about this is, of course, hydrogen is a very lightweight element. So these two are very small. If I had 50 grams of hydrogen, I would have a lot more atoms of hydrogen than, for example, if I had 50 grams of radium, which is an extremely heavy molecule, or atom, I should say. So pound for pound, even though this is only 3.2 MeVs, it still turns out to be a lot of energy because hydrogen is very lightweight. So a relatively small sample still in the long run will produce quite a bit of energy.